Welcome to this tutorial on runtime analysis of population-based evolutionary algorithms. My name is Kristian Lehre. I'm affiliated with University of Birmingham, and with me I have Pietro Oliveto from University of Sheffield. So this is a more advanced tutorial where we're focusing on more complex population-based algorithms, which are commonly applied in practice. So what we see in practice when we apply these methods is that often they depend quite strongly on their parameter settings. And when we just run experiments, it's difficult to understand why this happens and how we can fix the parameter settings. So just to illustrate this point, first I'm going to briefly describe an overall type of algorithms we're looking at, and then run some experiments with some visualization that show an example of this effect. So we'll see how the relationship between the selection pressure and mutation rate can drastically impact the performance of an algorithm. So that's just the introduction, and in the main part we're really going to focus on the theory that can explain under what circumstances population-based evolutionary algorithms can be efficient. So with efficient we mean they can find a solution in expected polynomial time. So just to make sure that everyone is on the same page, what are evolutionary algorithms? So these are nature-inspired search methods or optimization methods. We assume that we have a large search space of candidate solutions and a fitness function which allocates which gives an objective value or a fitness value for each solution, and what we want to do is to find among all these solutions a solution with high fitness value. So we start by initializing a population with individuals selected uniformly at random. Then we use the fitness function to select some of the better individuals. The selected individuals will become parents, so we recombine the genetic material in the parents. Then we apply some mutation operator, and this gives us some offspring. So these offspring are variations of the selected parents. So this is now repeated in several generations. So each cycle here is called a generation. So the hope now is that over time the population will improve and get better and better individuals. Okay, so here is an example of a specific evolutionary algorithm. So we have as input a fitness function which assigns a fitness value to every bit string of length n. We have a population size lambda, which is a parameter. We have a parameter for the selected pressure called eta in this particular case. This is just a value between 1 and 2. And then we have a mutation rate g over n. Okay, so to use this algorithm we need to choose 3 parameters: the population size, selected pressure, and mutation rate. So we start by choosing a population uniformly at random from the search space, and then we go into a loop. And we create, in each generation, we create lambda offspring. So first we select an individual from the current population using linear ranking selection. So it's not important the details of that selection mechanism now, but it selects individuals with higher fitness more often than individuals with lower fitness. And the degree to which this algorithm prefers the fittest individuals is determined by this parameter eta. So eta can be between 1 and 2, so if you have eta equals 1, you have just uniform selection, and if eta equals 2, you have a stronger bias towards the fitter individuals. Okay, so assume we have selected an individual x, then we apply bitwise mutation. So for each bit position, we flip it with probability g over n. So g is now this mutation rate. We obtain now the offspring, and this will be the ith offspring, and we do this lambda times to generate the next population. So a very simple algorithm. Okay, and most often with research in these algorithms we implement the algorithm and we do some experiments and collect some statistics. what we're interested in doing here is instead to see if we can prove something about this algorithm. So can we prove that this algorithm is efficient for various types of fitness functions? And this is quite challenging. So let's say we take a very simple fitness function like 1 max. So this is just the sum of the 1 bits in the bit string. So a priori this would be an easy problem. And the question is, how can we now choose these parameters such that the algorithm finds the optimal solution in polynomial time with respect to the size of the problem? A simulation of this algorithm which you can try out. So if you go to this URL, it's a bit small here, but you will see the link in the slides. Here we have interactive visualization of this algorithm. So here at the bottom we see the distribution of fitness values in the population. So for a given value I, we will see now how many individuals or what fraction of the population have this particular fitness value. So this x-axis ranges from 0 up to n. So what we see here now is that we have 0 individuals with optimal fitness n, and we have maybe around 95% of the 1 bits, we have some individuals that achieve that number of 1 bits. But we see that this algorithm somehow gets stuck in some kind of equilibrium. Okay, here we can choose the parameters of the algorithm. So on the x-axis I have the mutation rate, so this parameter t, and on the y-axis we have the selective pressure, which is just a parameter between 1 and 2. So now the question is, will this algorithm ever find the solution? And how can we choose these parameters so that the algorithm will find the solution efficiently? Okay, so with these parameters, mutation rate 1 over n and eta equal 1.5, it seems that this is something that's going to take a very long time to find optimum. So what we can see here now is that to find optimum we can increase the mutation rate, increase the selective pressure and decrease the mutation rate. So if I move something like here, see the population is moving towards the optimum. If I decrease the selective pressure, you see the population is falling back. And if I have a very high mutation rate, my solutions are only like 50% 1 bits. Okay, so this demonstrates that the behavior of this algorithm, even for a very simple problem, is highly dependent on the parameter settings. So the trick here now for this particular algorithm is that we need to choose, in order to find the optimum efficiently, we need to choose the mutation rate so that it is less than the logarithm of the parameter eta. So if I pick eta to be something like 2, I need to choose mutation rate something like 0.64 or something. Okay. Yes. So why this particular value? This is what I'm going to tell you in this tutorial. Okay, so just in general, it is a challenging problem to develop the mathematical methodology that can explain and predict the performance of evolutionary algorithms and of the heuristics. So this is quote is a quote from Papadimitriou and Staglitz's book from 98, where they state that this is one of the most important challenges facing the fields of optimization algorithms.
So this tutorial will cover population-based evolutionary algorithms. So you might ask, aren't all evolutionary algorithms population-based? Yes, perhaps, but early on in this field, it's quite common to look at very simplified evolutionary algorithms that don't have a population. So these are, for example, the 1+1 EA or RLS. In this tutorial, we focus on non-elitist generational EAs. We also have this other tutorial that focuses on steady-state elitist EAs. So the tutorial will provide an overview of the goals of runtime analysis of EAs, and we will focus on presenting techniques that are applicable in different scenarios. So this tutorial is good to attend if you want to understand the behavior of evolutionary algorithms and how you can change the design of the algorithm to improve its performance, to familiar yourself with the techniques in the area, and to initiate research in this area. So after the tutorial, you should have enhanced your ability to understand theoretically population dynamics of evolutionary algorithms and different problems, perform complexity analysis of population-based EAs and some combinatorial problems, and also understand how algorithms work on more complex rugged fitness landscapes. And you should have the basic skills to start independent research in the area. Okay, so this is an overview of this tutorial. So to start with, we'll talk about or introduce formally what do we mean by runtime analysis. And then we're going to look briefly at one very important technique within runtime analysis, which is called drift analysis. So using drift analysis, we can often obtain bounds on upper or lower bounds on the expected time for simple evolutionary algorithms to reach a global optimum. However, for population-based algorithms, more complex algorithms, especially those using crossover and so on, it's non-trivial to apply drift analysis directly. So instead we're going to introduce various tools that help us analyze these more complex algorithms. So to prove upper bounds on the expected running time, we will look at a general technique called the Levelbased Theorem. So this is a method to derive upper bounds on the expected running time of non-elitist generational EAs. So to introduce this technique, we're going to look into detail how it can be used to analyze a genetic algorithm on the 1max problem. And then we're going to look at more complex examples. So first we're going to look at what happens if we have some noise or uncertainty in the fitness function. And finally, we'll look at cases where these non-elitist generational EAs really shine. That's when we have fitness landscape with some degree of deception or ruggedness. So if you have a large population and you use non-elitism, often these algorithms can be quite effective. Then we're going to look at scenarios where these algorithms fail. So this can happen for various reasons. For example, if there is an incorrect balance between the selection pressure and the mutation rate in the algorithm. So we'll introduce a general technique to derive all of these results called the negative drift theorem for populations. Then we're going to briefly look at self-adaptation, and in the end we're going to look at negative drift when we use the crossover operator.
Okay, so just to put this into context when we talk about runtime, we first have to set up somehow the problem scenario for the algorithm. So when we analyze the runtime of evolutionary algorithms, we are usually using what is called the Blackbox Optimization scenario. Okay, so what we want to do is to model somehow the information which is available to the algorithm. So usually an evolutionary algorithm A, it's designed for some class of fitness functions f. However, when the algorithm optimizes a particular fitness function within this class, it doesn't use anything about the structure directly of the fitness function. Instead, it has what we call black box access to the fitness function. So it can take, for any step t, it queries for the fitness of some selected search point x1, and then we can assume theoretically that there is some kind of oracle that tells us, okay, what is the fitness value of that particular search point. And then based on that, the algorithm knows a little bit more about the fitness function, and it can ask for a new search point. Okay, x2, what is the fitness value of x2, and so on. Okay, so this kind of scenario might seem quite far away from how typical evolutionary algorithms work, but from a theoretical point of view, this is really essentially what the algorithm sees. It can manipulate search points, and it can obtain fitness values for particular search points. So this is to distinguish, for example, with gradient descent. For example, if you want to train a neural network, so in gradient descent you have a bit more information. So you have the gradients of each point as well. So here we only have access to the function values. Okay, so these black box scenarios now, almost all the evolutionary algorithms can be modeled as this. It basically just asks for fitness values of search points. So if we have now a particular algorithm A and a fitness function f, a concrete fitness function f, we say that the runtime of algorithm A on this fitness function f, it is the number of times that this algorithm queries the oracle for fitness values until it queries the optimal search point for the first time. So the optimal search point here is a search point xt such that for all other search points, or for all search points in the search space, we assume here that we have bit strings. The fitness of xt is at least as high as the fitness of y. Okay, so this is the best fitness we can get. Okay, so this is for one specific fitness function. But usually we are interested in understanding the runtime of the algorithm on a function class or a problem class. So now we take the maximum, so the runtime of the algorithm on the class is the maximum of the maximum runtime over any function in the class. Okay, now since this runtime, or since this algorithm makes random decisions, this will be a random variable. So when we define the worst case expected runtime of the algorithm, we take the maximum of the expectations of these random variables. Okay. And usually we're interested in understanding now how this worst case expected runtime depends on characteristics of the fitness function or the problem. So usually we're interested in understanding how it depends on the problem size. So the problem size is the number of bits for each search point, so n here, but also other aspects of the problem. And we're also interested in understanding how this runtime depends on the parameter settings of the algorithm. Let's say mutation rate, or population size, or other parameter settings of the algorithm. So this is the goal of runtime analysis, to do this for different algorithms and for different classes of functions. Okay, so this is a fairly well established area. There's been written several books on this topic. This green book here is now a bit old, so there's a new version of this book recently published. There's also a book by Neumann and Witt, which focuses more on combinatorial optimization problems. And there's also a book by Thomas Jansen on analyzing evolutionary algorithms. Okay, so theory of evolutionary algorithms have been around for a long time. And this area has developed in terms of the assumptions one make. So initially people made somehow unrealistic assumptions. For example, you assume that you have an infinite population size, or you can assume what happens if they run the algorithm in infinite time, so you're looking at the convergence of the algorithm. There's also different types of other assumptions that people use is that you don't have a parent population, or you have monomorphic populations. So for example, 1 plus 1 EA, you don't really have a population, you just have a single individual. So variance of this is 1 plus lambda EA or 1 comma lambda EA. So early research used Markov chain analysis, or classical tools for Markov chain theory, because most evolutionary algorithms can be described as a Markov chain. However, this approach is not so popular these days because very often these state spaces that you get with realistic evolutionary algorithms become very, very large. So it's very difficult to analyze directly, for example, or analyze directly the transition matrix that you obtain. So you need some other better tools. So very early tools is something called the fitness level technique, where you kind of coarse grain the search space instead of talking about every possible state that the algorithm can make. If you're looking at a coarse graining of states, so we'll talk about this fitness level technique. So for population based EA mu plus 1 steady state EA. There's also techniques based on stochastic dominance. Very important class of technique is something called drift analysis. I'll talk about that quite a lot. So this is built on martingale theory. There's also techniques using various notions of family trees. So you can look at the lineages of the individuals as some kind of family trees, and then you can analyze using probabilistic techniques the shape and distribution of these lineages. Related to this is multi-type branching processes, which can be used to prove negative drift theorem. So these are lower bounds. And there's also this level-based analysis, which was introduced some years ago. Okay, so the first technique we're going to talk about is called drift analysis. And this is one of the most important techniques used in this area. So I think you can take almost any paper published these days and it will use some form of drift analysis. So what is drift analysis? So imagine that you have some EA, and you can think of the state of the EA as some point in some state space. Okay, and in each generation the state of the EA changes. Okay, so you do some mutation or crossover and selection and so on. So for example, after generation K, the algorithm does something and then it moves in the state space. So this is some kind of abstract space, and often we want to figure out how long does it take to get into a particular region of the state space. For example, those states where we have an optimal solution in the population. Okay, so in principle, as I said earlier, we could use just Markov chain theory to analyze this directly. For example, to compute what is called the first hitting time into this set, this red set here. However, the state space is extremely large, so it's mathematically often difficult to analyze directly the state transition matrices that you get from this type of formulation. So what we do in drift analysis is that we introduce some sort of potential or distance function. So for each state, we map down the state to some real number. Okay, and the choice of the distance function depends on the particular application. So here we call the distance function d. Okay, so instead of having now a stochastic process in this huge space x here, we have a stochastic process on this real line. Okay, so at time k, we have a certain distance here, and at this next generation k plus 1, we have a new distance. And now what we call the drift is the difference in distance from k to k plus 1. So this is the drift at time k. So this is a random variable, and drift analysis is about predicting the long-term behavior of this process using properties of this random variable. So usually we want to say something about the drift that holds for all k. And if we can do that, often we can compute interesting properties about the process. For example, hitting time, so how many generations it will take to reach this desired region, or occupancy time. So for example, what fraction of steps are we within a particular region, or some stability properties of the process. So it's important to note that stochastic drift is a different concept than genetic drift in population genetics. It's an unfortunate clash between concepts, but stochastic drift is very well established in theory of stochastic processes, and also genetic drift is very much established in population genetics, so it's difficult to choose different terms here. Okay, so the simplest and the most fundamental drift theorem we have is the following. So assuming now that we are at some distance k, so dx of k, let's call this yk. So if for any step the expectation of the drift is less than something like minus epsilon, then we say that drift condition C1 is satisfied. Okay, so what does this really mean? It means as long as we haven't reached 0, on average we will move by epsilon towards 0. Okay, this is just expectation, so sometimes we might move to the right, sometimes we might move to the left, but on average we reduce the distance by epsilon. Okay, if this is the case, then the expected time to reach 0 is going to be the maximum distance b divided by epsilon. Okay, so here we assume that this stochastic process y1, y2 and so on is limited to this interval 0 to b. And here we define t to be the first time where we reach 0. So if C1 plus holds, then the expected time to reach 0 is going to be less than b divided by epsilon. We can have a related condition. So we say that the drift is at least minus epsilon. So it's minus epsilon or a number that is larger than minus epsilon. So it means we're not moving more than epsilon per step. So in that case, the expected time to reach 0 is at least y0, so the initial distance, divided by epsilon. And these theorems have been around for a long time, so they were introduced to evolutionary computation by Lehre and Yao in 2001. Okay, so let's look at an example of how we can apply this drift theorem. So here is a very simple fitness function. So it's one of those theoretical benchmark functions. So we have the leading one's fitness function. So imagine we have a bit string of length n. then the fitness is the number of leading 1 bits. Okay? Mathematically we can express it like this. Okay, now we can analyze how long will it take for the 1 lambda EA to find the optimum of leading ones. So what we will prove is that the 1 lambda EA, if you choose lambda to be n, it will optimize leading ones in big O n squared time, expected time. Okay, so to apply drift analysis, we first need to come up with a distance function, and often this is the most difficult part of drift analysis. So in this case, it's quite natural to say that the distance is the remaining number of bits that you need to set right. Okay, so it's n minus your current number of leading ones. Okay, so what is the drift in this case? So the drift is how much on average we change the distance. Okay, so let's assume now that the current distance is n minus I. Okay, so in order to reduce the distance by at least 1, it is sufficient that at least 1 out of lambda offspring do not flip any of the first I1 bits, and that we flip at the same time the first 0 bit in the bit string. So if we have at least one such individual, then we will have reduced the distance by at least 1. Okay. If that doesn't happen, so none of the individuals produces a better offspring, sorry, none of the offspring are better, then in the worst case we will reduce the distance by minus n. Okay, so a very rough bound is then, first we compute, okay, what is the probability that one particular individual improves the distance, so improves the fitness. So we just need to flip one single bit. We do that with probability 1 over n, and then we should not flip any of the leading 1 bits. Okay, and in the worst case this is n minus 1 leading 1 bits. Okay, so we have a greater than or equal symbol here. So this is the probability that one particular individual improves. Now the probability that none of the individuals improve, so we have lambda offspring, is going to be 1 minus all of this to the power of lambda. Okay, so this is the probability that none of the individuals improves. So if none of the individuals improves, in the worst case we have minus n drift. So this is the probability that at least one of lambda individuals has an improvement. So then we've improved by at least 1. Okay, and then we can use some standard simplifications, which says that 1 minus 1 over n to the power of n minus 1, this is at least 1 over e. And then we have 1 minus e over n to the power of lambda, which is n. This is again something close to 1 over e, so this is a constant. So all of this is going to be some constant c1, and the probability that none of the offspring improves, this is going to be, this is a constant, so roughly 1 over e. So 1 minus 1 over e is some constant, so this to the power of lambda is going to be some constant c2 to the power of n. Lambda is n, and c2 is less than 1, so this is exponentially small, so this is omega 1 drift. Okay, so the expected time, so the expected number of generations we need to find the optimum will be the maximum distance divided by the drift. So the drift in this case is omega 1, maximum distance is n, so this is going to be n, and then in each generation we evaluate lambda individuals, which is n, so we get n squared upper bound on the runtime. Okay, there's a whole range of possible drift theorems that depends on what kind of setting you are in. So we have talked about additive drift now, upper bound, lower bounds, but we can also have cases where we have zero drift. This is called, we have some kind of super martingales, or we have multiplicative drift, upper bound, lower bound, we have variable drift, and we also have population drift. So I won't have time to talk about all of these drift theorems, but there is a separate tutorial on this topic which you can find on my homepage. Okay, so now we're going to talk about non-elitistic generational evolutionary algorithms, and some techniques we can use to analyze the runtime of such algorithms. So first, let's look at how these type of algorithms work. Here's an example. So in this algorithm, we have a population of some individuals at some generation t. So in each generation, we evaluate the fitness of every individual in the population, and then we do the following lambda times. We select two parents from the population. So we have some selection mechanism that we choose two parents. So the selection mechanism depends on what particular algorithm you're using. It can, for example, be mu, lambda selection or Tournament selection. So we pick two parents, and then we apply a crossover operator or recombination to these two parents. We get some offspring, and then we apply mutation to this offspring. So crossover is typically that you select, if you have two bit strings, you select uniformly at random one of the bits from either parent with equal probability. Okay, so sometimes from the first parent, sometimes from the other parent. Bitwise mutation, typically we flip each bit with probability chi over n, where n is the number of bits. So independently. So chi now determines how much mutation we do. Okay, this is just one example of an algorithm. But there's a whole range of different algorithms. So we can plug in different selection mechanisms. So we have, for example, ranking selection, mu, lambda selection, tournament selection, and so on. We also have different ways of evaluating fitness. So for example, we have assumed that we have a deterministic fitness function, but we can also have noisy fitness function or stochastic fitness function, or we can have dynamic fitness function, or maybe also something called partial fitness function. We only see some of the bits. There's also a whole range of different variation operators, and we also have many different types of search spaces. So what we would like to do is to describe all such possibilities using one generic mathematical model. So what we see here now is that in each generation we have as input a population, and then we do something to that population to produce one new individual. And then we produce the next generation by repeating this process lambda times, where lambda is the population size. Okay, so many algorithms, many generational evolutionary algorithms work like this. So mathematically we can say that we have some abstract operator D that somehow describes everything in one, everything needed to produce one offspring from the current population. So this D will now contain selection mechanism, variation operators, maybe noisy fitness evaluations, and so on. So in an abstract sense, many algorithms can be described like this. So we have a search space X and some random operator D, which checks a population of size lambda and produces one new individual in X. So in the initial generation, we just sample uniform at random a population of lambda individuals. And then in each generation, we just sample lambda times independently and identically from this distribution D, which depends on the current population T. So our goal is now to define or introduce some general tools that allows us to analyze the runtime of such algorithms. Okay, so we need to know something about this D operator and the population size in order to do this. So this is where this level-based theorem comes into play. So the general problem is like the following. So we have some target set in the search space. Let's say we are interested in finding the global optima of some fitness function. So let's say the target set is some subset B of the search space X. Then we can define the runtime of this algorithm to be lambda times T, where T is the smallest generation number such that at least one individual in the population at time T belongs to this target set B. Okay, and we multiply here by lambda because in every generation we evaluate lambda individuals. Well, it depends on the type of algorithm you use, but most often you evaluate the population, all individuals in the population in every generation. Okay, and P0, P1, and so on, these are the populations that this algorithm generates. So at an from an abstract point of view, in this problem we're interested in finding out how does the expectation of this random variable depend on this operator D and lambda. Okay, so how much time will this algorithm need to obtain this target set B? Okay, so we have introduced this tool called the Levelbased Theorem, which says, okay, if this operator, the theorem essentially says this, if this operator D and lambda satisfy certain conditions, then this theorem will provide an upper bound on this expectation. Okay, so we need to provide some information about D and lambda, and if we can provide that information, then the theorem will give us the upper bound on the runtime. Okay, so I am now going to tell you what information we need about D and lambda in order to apply this theorem. So before I do that, I need to talk about some concepts. So we first have what is called a level partitioning of the search space. So given the search space X, we need to come up with some way of partitioning this search space into different levels. Okay, and this partitioning, or these subsets, must satisfy the following properties. So if I take the union of all the levels, we get the entire search space. And if I take the intersection between any two levels, I get the empty set. So these last two properties, these two first properties, they mean that, mathematically speaking, this is a partitioning of the search space. What I also need is that the last level AM covers the optima for the problem, or more generally, it covers B. Okay, so the last level AM here should be B. Okay, in order to talk about these levels, it's useful to introduce some notation. So we introduce this notation A subscript at least J to mean everything above level J, from level J and upwards. So for example, A at least 3 means this part of the search space here. It's level 3 and upwards. Okay. Then I also introduce some notation. So let's say we have a population of lambda individuals. So I can describe this as a vector of lambda elements in the search space. Okay. So let's say you have such a vector P, and then you have one level J. Okay, for example, 4. Then by abusing notation a little bit, I say that P intersection A at least J, so the cardinality of that set, is basically the number of individuals in my population P that belongs to level J or upwards. Okay, so if the population are here, these dots here, then P intersection A at least 4 equals 5, because 5 of the individuals in the population belongs to set 4 or higher, level 4 or higher. Okay, so I have talked now about levels, and I've talked about this notion of computing, okay, how many individuals do I have at a certain level or higher. Then I can talk about what is the current level of the population. So I'm using the notion of current level to capture the state of the population. So I want to figure out roughly how far has the population progressed at a given point in time. So first we need to specify some parameter gamma naught. Okay, it's some number between 0 and 1. So we define the current level of population with respect to some fraction gamma naught. So let's say it can be 1/2. So once we've specified this, then we can define the current level of the population to be the unique integer j, such that we have okay, this is actually wrong, it should be the other direction. We have at least, sorry, this is right. We have the number of individuals in level j or higher is at least gamma naught lambda. However, the number of individuals in the population at level j plus 1 or higher is strictly less than gamma naught lambda. Okay, so let's say now that we choose gamma naught to be 1/2. So what is the current level here? So in order to be the current level, we have to have at least half of the population in level j or higher, but less than half of the population in level j plus 1 or higher. So let's say here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here the current level is 4. Because we have 5 individuals, which is half of the population in level 4 or higher. However, the number of individuals in level j plus 1 or higher, so 5 or higher, is 2, which is less than lambda divided by 2, so half times lambda. Okay, so now I'm ready to state the conditions of this theorem. So this is what we need to know about this operator D in order to say something about the runtime. Okay, so the conditions are G1 for any population P and some individual. So if we sample now an individual using our operator D, then the probability, so if the current level is J, then the probability that we sample something in the level above or better should be at least Zj. So Zj is now a parameter of the theorem that you have to find. Okay, so if you look at this figure here, so here is the search space, this red figure is the population. Let's say we have gamma naught lambda individuals in level J or higher. And if this is the case, let's say the distribution of the level is shown here in blue. So the probability now that we end up in level J plus 1 or higher is kind of indicated by this part of this distribution. So this, we need to have some lower bound, that given that the current level is J, we need to have some lower bound Zj of producing something that is in the next level. So it should be non-zero probability of producing something that is better. Okay. At the same time, if we already have gamma lambda individuals in the level above the current level, so for any gamma less than gamma naught, the probability that we sample an individual in level j plus 1 or higher should be at least gamma times 1 plus delta for some positive delta. Okay, so if the current level is j, we should have, in expectation, we should increase the fraction of individuals in the next level by a factor of 1 plus delta. So this is condition G2, and condition G3 says that we must assume that the population size is not too small. Okay, so we must assume that the population is at least this quantity. So this quantity depends on m, so this is the number of levels. It depends on gamma naught, which we have from the definition of the current level. It depends on delta, which determines how this multiplicative factor here. And it depends on z min, which is the smallest of these upgrade probabilities here. Okay, in typical applications, gamma naught is a constant, delta is a constant, and z min is some polynomial in n. So then typically it suffices to choose a population size that is some constant times log of n, so the number of bits. Okay, so if these three conditions are satisfied for all populations, then the expected time to reach the last level is given by this expression here. So it depends on the population size, and it depends on the upgrade probabilities, and it depends on this multiplicative factor here, delta. So the runtime, the bound will increase if lambda increases, and it will increase if zj, these upgrade probabilities, are smaller. It will also increase if delta is smaller. Okay, so this is a very general theorem that you can apply for many different algorithms and for many different settings. So it was used to analyze evolutionary algorithms with crossover operators. So this was, earlier it was quite tricky to analyze such algorithms, but using this technique it's in some settings fairly straightforward. We can also use this to actually design evolutionary algorithms. So we can come up with some kind of generic class of evolutionary algorithms, and then for a particular type of problem we can figure out, okay, how should we design the EA or the components of this algorithm in order to satisfy the conditions of the level-based theorem. So this was, for example, used to design algorithm to compute shortest paths with genetic algorithms. It's also been used to analyze evolutionary algorithms where you have noisy fitness functions, or partially observable fitness functions, or also dynamic fitness functions. There's a whole range of work on using this for analyzing estimation of distribution algorithms. And recently we also applied it to analyze self-adaptive evolutionary algorithms. So this is where some of the parameters of the algorithm is encoded in the genome of the individuals. Okay, so let's say you have a population-based algorithm that fits within this generic mathematical description I mentioned before. How can you use this theorem to produce some bounds on the runtime of the algorithm? So these are the steps that we recommend that you follow. So the first thing you need to do is to define a partition of the search space where the levels to some degree reflects the state of the algorithm, and the last level should consist of the goal state or the target state. Then we suggest that you start by trying to see if condition G2 is verified. So it means that you need to try to choose parameters gamma naught and delta And you might also have to configure the algorithm by choosing, let's say, mutation rate and selective pressure, such that condition G2 is true. Okay, so assuming that you have gamma lambda individuals in the level above the current level, then in the next generation you obtain a new individual in the next level, j plus 1, with probability at least gamma times 1 plus delta. So this is typically where you have to tune the selective pressure and the mutation rate. Once this is true, often it's then quite straightforward to compute a lower bound on the probability of producing a better individual. Okay, so usually it means you have to select one of the individuals in the current level. So usually that happens with constant probability, because you assume that you have a large fraction of the population, or a gamma 0 fraction of the population in the current level. And then you need to do the right mutation and crossover operation to go to the next level. Then you need to, given these parameters, gamma naught, delta, zj, you can then compute how big population size do you need. As I said, usually it suffices with something like log n population size. And then the final step is just to plug in all of these parameters into this expression here to obtain the upper bound on the runtime. Okay. Now, how tight is this theorem? So, is it the case that this expression is a good approximation, or does this really reflect how much time the algorithm needs to find the optimal solution? Well, it depends on how you choose to define these levels, and how well you can compute these probabilities, upgrade probabilities, and this delta. Okay, so let's say that in a particular application you have chosen a particular partition A, and you have chosen a parameter gamma naught and a parameter delta, and this upgrade probability Z. Okay, then your algorithm, the theorem will tell you, okay, the upper bound is no more than this. Okay, but it might be that your algorithm is actually much faster than this. It could be that you have been very inaccurate in computing this upgrade probabilities, for example. So there's another theorem. This is a lower bound. It says for some given parameters A, gamma naught, delta, and Z, there exists at least one algorithm that satisfies condition G1 and G2 for these parameters, that has runtime at least this, right? So it means that for the parameters you obtain for your algorithm, there exists some other algorithm that is not very fast. I mean, that has roughly the same runtime as this upper bound here. So this means that this theorem is essentially almost tight. Okay, there is some differences here. There are some differences. So here we have delta square. In the lower bound we have delta, and there's some slight differences here in the constants. Okay, so as I said, for a given set of parameters, it is possible that your algorithm is faster than this. However, in order to prove this, you need to provide more precise parameters. Okay, because the only thing that this theorem knows about your algorithm are those parameters. So this lower bound from this theorem here gives you the best possible runtime bound that you can achieve with these parameters. So if your algorithm really is faster, then you have to provide more information, perhaps with a better, more precise set of parameters, or different level settings or a different way of characterizing algorithms than this. Okay, so let's now try to apply the level-based theorem to a very concrete example. So we have an algorithm which we called mu, lambda genetic algorithm. So how it works is that it first, in each generation, to produce an offspring Y, it selects two parents uniformly at random among the mu fittest individuals in the population. So we have a population size of lambda, and then we choose among the mu fittest individuals, we just choose uniform at random an individual. So to select two parents, we choose two such parents, and then we use uniform crossover. So this, as I explained earlier, we produce an offspring Z, where the offspring has a 50% chance of inheriting the bit from either of the parents. After that, we apply mutation, so bitwise mutation with probability G over N, and then we get some offspring Y. Okay, so this is how the algorithm works. To produce each offspring Y, we do these steps: selection, crossover, and mutation. And then we do this lambda times to get the next generation. Okay, what we're going to do is to analyze this algorithm on a function called 1max. So 1max is somehow the simplest fitness function we can think of. It's just, we just count the number of 1 bits in the bit string. So obviously the optimal solution is a bit string with all 1 bits. Okay, the theorem we want to prove is the following. So if lambda is at least c times log n for some sufficiently large constant c, and the ratio between lambda and mu is at least 2 times e to the power of g times 1 plus delta for some constant delta, then the expected runtime of this algorithm is n times lambda. So the expected runtime is n, which is the length of the bit string, times lambda, which is the population size. And we need to choose now lambda to be something like a constant times log n. So the runtime is in the order of n times log n. So this is typically what we get with evolutionary algorithms on this fitness function. Okay, so how can we prove this? So let's look a bit at the selection mechanism. So we have a particular time, let's say time 0, we have lambda individuals. We sort all the individuals according to fitness, and then we pick uniformly at random from among the mu best individuals. Okay, now in order to use the level-based theorem, we need to partition the search space into levels. So the most straightforward way of defining these levels is to use directly the fitness values. So we say that we are in level j if the number of 1 bits in a bit string is j. Okay, so it means that we will get n plus 1 levels. So from level 0 up to n. Okay. The first difficulty we need to face when analyzing this algorithm is how to deal with crossover. So, let's say now we have two individuals. Let's say we have an individual in level j plus 1, and we have an individual in level j or higher. Okay. So now, if we add together the number of 1 bits in x and the number of 1 bits in y, these two individuals, by the definition of these levels, the number of 1 bits in these two bit strings must be at least 2 times j plus 1. Okay. let's say now that instead of producing one offspring, we produce two offspring. Okay, so the first offspring will be produced by, as normal, we choose uniform at random a bit from one of the parents. So for example, this offspring u here, now we have chosen this bit from the second parent. Now the other offspring will choose the opposite bit, right? So if u chooses the bit from y, then v inherits the bit from x. So here we get 0 and so on. Okay, afterwards we just select uniformly at random either u or v. So this kind of way of defining the crossover operator is exactly the same as standard uniform crossover. So what we have now is that the number of 1 bits in x plus the number of 1 bits in y must equal the number of 1 bits in u plus the number of 1 bits in v. Okay, so there are no bits are lost here in this process, going through here. Okay, so let's now assume, without loss of generality, that u is the bit string that has the most 1 bits. Okay, so u plus v is less than 2 times the number of 1 bits in u. Okay, by this assumption. So it means that the number of 1 bits in u is going to be at least j plus 1/2. Okay, and since we can't have half 1 bits, we must have in u have at least j plus 1 bits. Okay, so this means that if we take crossover between two parents, one with at least j 1 bits and the other with at least j plus 1 bits, then with probability 1, the fittest of the offspring will belong to j plus 1. Okay, so the probability now that when we do crossover between two such individuals, the probability that we select u, the fittest, will be at least 1/2, because we select this uniform at random between these two individuals. Okay, so the probability that after crossover now, with such parents, that I get at least an individual in j plus 1 is at least 1/2, and we call this parameter just epsilon here. Okay, so now let's look at condition G2. So let's recall the assumptions of G2. So we have a population P. We assume that we have at least gamma naught lambda individuals in level J, and we have less than gamma naught lambda individuals in level J plus 1 or higher. Okay, and I'm going to choose now gamma naught to be mu divided by lambda. So I will show that this will be a clever choice later. So to draw this population here are the fitness values. I have some individuals, so this is a histogram of the fitness values of the population. So I have at least gamma 0 lambda individuals in fitness level J or higher, and I have at least gamma lambda individuals in fitness level J plus 1 or higher. Now, why did I choose gamma naught to be mu of lambda? Well, it means that I know that I have at least gamma naught times lambda, which equals mu individuals in fitness level J. So when I do mu comma lambda selection with probability 1, I select an individual within this blue region here. So for sure, I definitely select an individual with fitness J or higher. And the probability that I select an individual with fitness J plus 1 or higher is just going to be gamma times lambda divided by mu, because I select uniformly at random among the mu best individuals. Okay, so the probability now, that's Z. So let's compute first the probability that the offspring from crossover is in level j plus 1. Then it's sufficient that first I select an individual in level j, and I select an individual in j plus 1, and then the offspring belongs to level j plus 1. Okay, so the probability that the first individual selected belongs to level j is 1, as I've shown earlier, and the probability that the second individual belongs to j plus 1 or higher is going to be gamma lambda over mu. Gamma lambda over mu. And the probability now that crossover operator produces an individual in j plus 1 is going to be this epsilon, or 1/2, which we looked at in the previous slide here. Okay, so in overall, after the probability that is z before mutation that we have an individual already in j plus 1, this is going to be something that is gamma lambda over mu divided by 2. Okay, but I'm interested in the final step here. I want to have, after mutation, I want to have an individual in with fitness j plus 1. So it's sufficient to first obtain an individual z which belong in j plus 1, and then mutation doesn't flip any bit. So this is this probability here. Okay. So if I now assume that lambda is at least 2 times mu times 1 minus g over n to the power of minus n times 1 plus delta. So this is roughly 2 times mu times e to the power of g. Then all of this is going to be gamma times 1 plus delta times 1 minus g over n times minus n. So this factor cancels, and I end up with gamma times 1 plus delta. So this is an example where you see that to satisfy G2, I have to choose the parameters of the algorithm correctly. So I have to choose the selective pressure here. So this selective pressure depends on the ratio between lambda and mu. Relative to the mutation rate, I have to choose it such that in the end I end up with a probability gamma 1 plus delta of producing individual in j plus 1. Okay. So this is condition G2, usually that's the most difficult. Then condition G1. Here it suffices that I just pick 2 individuals in level J. So in this case I don't know whether I have any individual in J plus 1, but it suffices that I pick 2 parents in level J, and then with probability 1/2 the offspring will be in J, and then I have to mutate the bootstring so that I obtain an individual in J plus 1. So I have the same kind of calculations, but now I have to rely on the mutation operator to do an upgrade. So the probability of upgrading will be n minus j, because this is the number of 0 bits I have, times the probability of flipping a 0 bit, times the probability of not flipping any other bits. So this is the probability that if I have an individual in j, I obtain an individual in j plus 1 by flipping one of the n minus j 0 bits. Okay, so with some calculations this is going to be something on the order of 1 minus j over n probability. Okay, so when I am very close to the optimum, this probability becomes quite small because there are very few 0 bits left. Okay, so just to repeat, G1, I have to produce a lower bound on the probability of producing some individual in level j plus 1, assuming which is always the case, no matter how many individuals I have in any levels above. And if I have any individuals in the levels above, so gamma lambda individuals in the level above, I should have a probability gamma times 1 plus delta producing such an individual. Okay, and the population size should be lower bounded by this expression. If this is the case, this is an upper bound on the runtime. So in my case now, if you look at this part of the expression, Okay, we ignore lambda first. So let me see, we have lambda outside. Yeah. Okay, so let's look at this summation here with just respect to this log terms here. So if I do a very simple simplification, so I just say, okay, this denominator here, it's lower bounded by the constant 4. Okay. Then I get that this sum is less than or equal to log of delta times lambda. Okay, and I have like n levels here. So this is n times log lambda. Okay, so this upper bound is imprecise because I do not explain that the upgrade probabilities Zj are large for small j. Okay, so if j is very small, I have many 0 bits. So then this expression becomes quite large. Let's say j equals 1, then you have a linear number. I have something like theta of n here. So to be a bit more precise, I can say, okay, this expression is going to be upper bounded by log of 6 over zj. So I ignore this 4 here. And this I can write as Cn divided by n minus j, where c is 12 times e to the power of g divided by 1 minus delta t. So this is what I obtained from the previous calculations. Okay, and this is going to be the factorial. So I have n minus j equals 0 up to n minus 1. So I get log of Cn to the power of n divided by n factorial. And then I can use the lower bound for n factorial, so this is no more than n over e to the power of n. So what I get here now is that n to the power of n cancel with n to the power of n. So I get log of c e to the power of n. So this is n times log, and then a constant. So this is n. Okay. I also have to bound this term. So here I can use the harmonic numbers. So the summation of 1 over e, I equals 1 to n, is big O log of n. So the second term can then be bounded by 1 over zj, which is big O n over n minus j. So this will be big O n log n. So in overall, I get a runtime which is n times lambda plus n times log n. And lambda is by assumption at least log n. So this is in overall n times big O n times lambda. Okay, so we can use a similar type of analysis for many other settings. For example, if you have noise. So let's say we use tournament selection. We pick 2 individuals and we compare those 2 individuals based on their fitness, and then we might have some probability of doing something wrong. Perhaps because you get some noise on the top of the fitness. But let's assume now that if we pick 2 individuals, x and y, and let's assume that x is strictly better than y with respect to the fitness, if the probability in this setting that x wins with probability 1/2 plus delta, then it's sufficient to choose a mutation rate delta over 3n, and assuming that 1 over delta is poly over n, to get polynomial runtime. So this means that even if it's a very high degree of noise, by choosing a low enough mutation rate and strong enough selective pressure, be able to optimize the function in polynomial time.
So far we looked at very simple fitness landscapes like 1max. Now we're focusing the attention on much more complex fitness landscapes where we have a high degree of ruggedness. And this is an example where actually non-elitist evolutionary algorithms really shine, so they can overcome a large number of local optima. So this is very recent work. It will be presented at the theory track this year's GECCO. So fitness landscapes of complex combinatorial optimization problems have typically several local optima surrounded by fitness values. And we believe that one feature of fitness landscapes that contribute to the difficulty is the sparseness of the local optima relative to the fitness values, to the density of the surrounding fitness values. So these are kind of the intuition behind the definition that we're going to propose here now. So we said that the Hamming shell at radius r around a bit string x is all bit strings at distance r from x. So it's easy to see that the size of the Hamming shell is n choose r. So we say that our set A is alpha dense with respect to a set A prime if the following holds. So for any element x in A, the fraction of the Hamming neighbors of x that belongs to A prime needs to be at least alpha. Okay, so let's look at the definition of an epsilon sparse set B. So here in this illustration, these blue regions correspond to the set B. So now we say that B is epsilon sparse if for all x in B and for any radius r, so let's say this is x. If you're looking at the fraction of elements in Hamming sphere at radius r around x that falls within B, it should be at most epsilon. And if we pick any search point x outside B, and we're looking at the fraction of elements in Hamming sphere with radius r around x that falls within B, it should be at most 1 over n fraction. Okay, so let's now define the problem class. So we say that the pseudo-Boolean problem belongs to sparse local opt alpha epsilon if we can construct a partition of the search space into a polynomial number of levels satisfying these 4 conditions. So for the full details I recommend to read the paper, but I will here focus on the most important condition. So now these levels should broadly follow the fitness values. However, we say it might be impossible to construct such a perfect level partition. So we say that a pair of levels AI and AJ are F-deceptive if AI comes before AJ, and there exists a search point in AI which has fitness at least as high as some search point in AJ. Okay, now call this the first element of the pair, we call this the fitness peak, and the second pair we call it the fitness valley. Okay, so what we require is that if we collect all such pairs and we take the union of the fitness peaks, we require that these are epsilon sparse. And if we take any fitness valley, we require that the fitness valley is alpha dense with respect to AJ and levels above AJ. This means if I'm in a fitness valley, at least an alpha fraction of my neighbors are within level J or higher. So if you look at the roles of alpha and epsilon, these are in some sense constraints on what problems can belong to the class. So if you choose epsilon very small, it means that any local optimum has to be very sparse. And if you choose alpha very large, it means that the fitness values needs to be very dense. In the other extreme case, where alpha is 0 and epsilon is 1, we essentially have no restrictions on the local optima and on the fitness values. So, by looking at sparse local op for different values of alpha and epsilon, we get a kind of a problem hierarchy. So I'm trying to draw this now in 2 dimensions. So on the x-axis I draw 1 minus alpha, and on the y-axis I have epsilon. So the closer I get to 0 on the x-axis, the stronger requirement I have on the density of the fitness values. And the lower I get on epsilon, the sparser the local optimum has to be. Okay, so sparse local opt alpha epsilon is essentially all the problems that fit within this these constraints for the value of alpha and epsilon. So clearly, if I choose now a larger alpha, a smaller alpha, and larger epsilon, so let's say alpha prime and epsilon prime, I get a larger problem class. So we can now classify problems and problem classes within this square. So 1 max, we have really no local optima, so we can put it down here into the simplest corner. Needle in the haystack, it is kind of deceptive in some sense, so the only way we can put it is here at the upper right corner. And other problems, if you look at some instances, for example knapsack, you can find that there are some intermediary here. Later we're going to look at a particular problem called BB funnel that has 2 parameters alpha and epsilon that coincide with this sparse local opt alpha epsilon here. So we now consider a class of non-elitist evolutionary algorithms. So this algorithm uses a ranking-based selection mechanism. So we describe this in a very general form. So we imagine that the algorithm has a function beta, which is a cumulative density function. Now, so to select an individual, the algorithm sorts the population according to fitness, with the best fitness first, and then it now samples the index I such that the probability that I is less than gamma lambda equals beta gamma. Okay. Once it selects an individual, it applies mutation, so bitwise mutation. So each bit is flipped with probability chi over n. So by repeating this lambda times, we produce a completely new population, and we just continue with the next generation. So as a second result of this paper, we will see conditions, sufficient conditions, where non-elitist algorithms are efficient on this sparse local opt problem class for a wide range of alpha and epsilon. So the first condition says that there should exist some psi naught such that for any gamma above psi naught, beta gamma is less than this function u of gamma. Okay, that's something that depends on epsilon and the mutation rate. The second condition says that for all gamma between 0 and gamma naught, beta gamma should be at least this function L gamma, and this is a function of the mutation rate. Okay, so if you observe here now, L gamma is larger than U gamma. So this means that the only way for this beta function to satisfy both conditions is that it's non-linear, right? Any linear choice of beta is going to fail. Final condition says that beta of psi plus gamma minus beta of psi should be at least this quantity. Okay, if these 3 conditions are satisfied, then the algorithm will have polynomial time. We assume now logarithmic population size bounded by some polynomial. And we can find positive examples of this for particular settings. So for example, if you use two-limit selection with tournament size 3 and use mutation rate parameter chi 1.09812, so this is quite close to the to the error threshold, a little bit below the error threshold, which is log of 3. Then, if you choose alpha to be at least 1/4 and epsilon to be less than 7 divided by 10 to the power of 5, then the conditions are satisfied. Another selection mechanism, if you use linear ranking selection with parameter eta equals 2, if you choose the mutation rate a little bit below the error threshold, which is in this case is log of 2, and alpha is at least 4/9 and epsilon is 1/100, then linear ranking selection will also satisfy this. But as I said, if you try to satisfy these conditions using mu comma lambda selection, which has a linear beta function, you will not be able to succeed. Assuming now the algorithm satisfies these conditions, we can analyze the relationship between two stochastic processes. One representing the number of individuals which are on the local optima, and the second process is how many individuals we have in a fitness value. So what we can prove is that if the selection mechanism satisfies the conditions, the proportion of individuals on the local optima will gradually decrease down to some, at most a fraction psi naught. And then once we have no more than psi naught individuals on the local optima, and we have some but not too many individuals in the fitness valleys, the probability of sampling an individual in the fitness valley becomes xt over lambda times 1 plus delta, where xt is the number of individuals we have in the fitness valley. So essentially, the proportion of individuals in the fitness valley will increase. And this is essentially condition G2 in the classical level-based theorem. So to finish everything, we apply the level-based theorem. Now, one difficulty is that we're not able to prove G2, condition G2, for individuals in the fitness valley if you have too many individuals on the peaks. So we introduce a generalization of the level-based theorem where we take into account deceptive regions B. Okay, so in this new theorem, G2 only needs to hold if you have not too many individuals on the peaks or on the deceptive region. So we will then have another condition, G0, which says that if you have too many individuals on the peak, they will eventually reduce. Okay, so far we've talked about how we can prove upper bound on the runtime. Now we're going to look at lower bounds. So in many cases we're interested to show when evolutionary algorithms are inefficient, so that they need a lot of time with high probability to find a target set or to find some optimal solutions. Okay, so I'm going to present a technique called negative drift theorem for populations. Okay, so again, the problem is like this. I have a sequence of populations over some search space X, and I have some target region. Here I call it A. So the target region could be, for example, the optimal solutions. And again, I define the time of the algorithm to be lambda times the smallest t, such that at time t I have an individual in set A. Okay. Now, what I'm interested in proving is to say this is going to take a lot of time. So I'm interested in prove bounds on the following form. So here I'm not talking about expectation, but I'm proving, analyzing the probability that this time will be less than some expression Tn. And I want to find for what Tn is it exponentially unlikely that I spend Tn time, that it suffices with Tn time. Okay, so for example, if Tn is an exponential function, then this expression says the probability that the algorithm will finish within exponential time is exponentially small. If you can prove a statement like this, it basically means your algorithm will, for all practical purposes, never find the optimum unless n is really, really small. Now, proving lower bounds is much harder than proving upper bounds.
So we'll prove an easy to use method that is applicable in many situations. However, here we're not in this very general scenario where we have an algorithm that takes an operator D. So here we're restricted to a bit more smaller set of algorithms where we have first selection and then variation. So we will prove theorems about algorithms on this form. So we have a selection mechanism. So in each generation we select the parent X from the current population T according to some probability distribution of the search space. And then we flip each bit position in X independently with some probability. Or we apply some variation operator. And then we say that the ith offspring is now going to be the result of doing this mutation. And then we do this lambda times to produce the next population. So we have to assume that population size is a polynomial in n. So if it's exponentially large, we use already exponential time in the first generation. We assume now that we have bitwise mutation with probability g over n, but there's no crossover. And we assume that we have some selection, nonelitistic selection mechanism. So for example, mu comma lambda selection, tournament selection, fitness proportion selection, ranking selection. And we assume that this selection mechanism satisfies some mild conditions that we'll talk about later. Okay, so again, what will be very important is the notion of selective pressure. So here we define what is called the reproductive rate. So first, the reproductive rate of an individual X in a population is lambda times p cell xi. So this means the expected number of times this individual will be selected in one generation. Okay. Now, then we talk about a reproductive rate of a selection mechanism. So we say that the reproductive rate of the selection mechanism is bounded from above by a parameter alpha naught is if for any population and for any search point or any individual in the population, the reproductive rate is less than alpha naught. Okay, it means if the reproductive rate is bounded from above by alpha naught, it means that in expectation, no individuals get more than alpha naught offspring. So let's take an example. Here again we have mu comma lambda selection. So mu comma lambda selection, we only select among the mu individuals, but we select uniformly at random among such individuals. So the probability of selecting any individual is either 0 if it's worse than the mu ranked individual, or it's 1 over mu if it's one of the mu fittest individuals. So this means that the reproductive rate for mu comma lambda selection is bounded by lambda over mu. This is the expected number of times any individual is selected among the mu best individuals. Okay, so informally, this is what the negative drift theorem tells us. We want to compute the time to reach some search point x star. Okay, we introduce two distances a and b. And what we need to prove is that any individual, for any population pt, any individual which is within distance at least a, but at most b, will have reproductive rate alpha naught less than e to the power of g. Okay, so essentially, if this condition is true, then it takes exponential time to reach within a of the target x star. This is essentially what the theorem says. So this is a bit more mathematical precise description of this theorem. So I won't go into detail here, but we have like three conditions. So we have a condition on the reproductive rate of individuals within Hamming distance between A and B to the target. We have a condition on the reproductive rate, so this shouldn't be essentially larger than e to the power of chi, so this is condition 2. And there's also a condition on how large b can be chosen. Okay, it has to be in this interval. So if these conditions are true, the probability that we will spend less than exponential time in the size of this interval is going to be exponentially small. Okay, so when are these conditions true? So these conditions are true in several different settings. So it can be true if okay, so let's look at an example of how we can apply this theorem. So we consider now a fitness function which is called needle in the haystack. So needle in the haystack is a problem where one specific bit string, let's say for example all 1-bit string has fitness 1 and all other individuals have fitness 0. Okay, so this is a classical problem that EAs can't really solve. So what we can prove using this theorem is that the optimization time of any non-elitistic EA with any selection mechanism on needle is going to be exponentially large with exponentially high probability. Okay, how can we prove this? Well, let's say that we have a fitness function as a selection mechanism that satisfies the following. So if x has higher probability than y, then the probability of selecting x must be higher than the probability of selecting y. So this means better individuals are selected more frequently. So this is what you can expect from most selection mechanisms. And if you can also assume that if you have two individuals with the same fitness, then they're selected with equal probability. So it means ties are drawn randomly. So if you have these two conditions, and then you can show that, okay, the individual which has fitness equal to the lowest fitness in population, it cannot have higher reproductive rate than 1 over lambda, or it cannot have higher reproductive rate than 1, right? So by A and B, the probability of selecting an individual X is going to be the same as the probability of selecting an individual with the lowest fitness. Okay, and the selection probabilities, they equal 1. So this is larger than lambda times the minimum selection probability, which is the probability of selecting individual X. So from this we have that the probability of selecting individual with fitness selecting individual X is at most 1 over lambda. So reproductive rate is at most 1. Okay, so we can now apply negative drift theorem with A equals 1. We can use choose alpha naught to be 1, because any individual which is not in the optimum will have reproductive rate 1 by the previous calculations. So we can choose psi to be log alpha over chi plus delta, which is delta, because log of 1 is 0, and delta is less than 1 for all chi, if you choose delta less than 1. So then we can just choose appropriate parameters for b, and then we obtain that it takes exponential time to reach within distance b of the optimum. You can also use this to prove that it takes long time. So suppose we have the jump function here for a large k, it will take long time to optimize this. So I won't have time to talk about this in detail. Okay, there's a different setting where the best individuals have low reproductive rate relative to the mutation rate. Okay, so this means if we have selected insufficient selective pressure. So, for example, in tournament selection, if k is less than e to the power of chi, then any individual has reproductive rate less than e to the power of chi. Or in mu comma lambda selection, if lambda is less than mu times e to the power of chi, then any individual have reproductive rate less than e to the power of chi. Okay, so this is related to a notion called the error threshold. So the error threshold is the case where you have too high mutation rate, chi, relative to the selective pressure. So then no matter what fitness function you use, it's going to take exponential time to reach a unique global optimum. So for example here, we have already looked at leading one's problem. So here is an upper bound that we can compute using the Levelbased Theorem, and here is a lower bound that we can compute using negative drift theorem. So here we see that we have some kind of phase transition. If we have selective pressure here on the y-axis, so the ratio between lambda over mu, if lambda over mu is close to 1, we're getting closer and closer to uniform selection, so low selective pressure. So if the ratio between lambda over mu is below a certain threshold, then we go from polynomial to exponential runtime. So this is like a sharp threshold here. Okay, there are other example applications of this negative drift theorem, which I won't have time to talk about here. We also have. Okay, I'll briefly talk about another application of this of both the Levelbased theorem and negative drift theorem population. So this is self-adaptive evolutionary algorithms. So this is algorithms that somehow changes their parameters while they're running. So there are two broad ways of doing parameter settings. What we've talked about so far is that we choose, before we start the algorithm, you choose some parameters. The way we can do that is to try different parameters in different runs and then pick the best algorithm over the runs. Or we can, during the runs, we can change the parameter while we're running. So there are different categories here. We have deterministic parameter control, where the parameters follow some deterministic settings. So for example, in similar to annealing, you have adaptive parameter control, where there's some kind of external algorithm that observes the process, and based on some statistical measures of what the population is doing, it changes the parameters. We also have self-adaptation, where the parameters of the algorithm are encoded in the genotype of the individuals. So one interesting question is whether these self-adaptive EAs can control parameters effectively. So for example, can we have settings where if you only use a fixed parameter setting, then we get exponential runtime, or if we uniformly mix parameters, then we get exponential runtime, but if we self-adapt parameters, then we get polynomial runtime. If we can find such a problem, it would be evidence that self-adaptation can be useful. So here is a simple example we looked at. So we have, in this case, only two different parameter settings. We have high or low mutation rate. So we have a mutation rate G1 or a mutation rate G2. So we have a population where each individual is a bit string and an extra gene for the mutation rate. We select, here we're using tournament selection, so we choose two parents uniformly at random. We pick the best parent. So the fitness obviously only depends on the bit string. And then with some probability P, we mutate the mutation rate. Then we apply mutation to the bit string with the current mutation rate. Okay, and then we get some offspring. And importantly, the mutation rate is inherited by the offspring. So in some sense, we're extending the search space. So the original search space is the bit string of length n, but we add now also a gene which specifies the mutation rate. Okay, here is an example where we have a peaked fitness landscape. And we assume now that the population starts on the peak. And we will prove, we can prove that the self-adaptive mechanism will actually be more efficient. So this is the definition of fitness function. It's not so important exact definition, but we have a peak here, and we need to overcome this peak to get to the optimum. So this is what happens in different scenarios. If you have a fixed low mutation rate, we have exponential runtime. Fixed high mutation rate, we have exponential runtime. If you have uniform mixing between two mutation rates, then we also have exponential runtime. But if we have self-adaptation, we get polynomial runtime. And if we try something like mu plus lambda EA, again we have exponential runtime because we're not able to escape from the peak. So I can demonstrate how this algorithm works. So this is what happens if I choose low mutation rate. The population is not able to jump off this peak. Well, some individuals will jump off the peak, but they have lower fitness than these guys. If I have only high mutation rate, the individuals will fall off the peak, but they are kind of above the error threshold. So the mutation rate is so high that I'm not, relative to the selective pressure, that I'm not able to actually move up to the top here. If I use self-adaptation, you see that the population in the beginning chooses high mutation rate, and then eventually the mutation will switch to low mutation rate, self-adapt to low mutation rate, and it will be able to climb up to the optimum. Okay, I've done with this part. Okay.
Okay, so Kristian has introduced the negative drift theorem for populations, which is a very general tool that can be applied to prove exponential lower bounds on the runtime of population-based algorithms, but it can only be applied with mutation-only algorithms and not with algorithms using crossover. So now I will show how it is also possible to analyze generational genetic algorithms that use both populations and crossover. However, we don't have a general method, and the analysis has to be more tailored towards a specific algorithm. As a proof of concept, we will analyze the standard simple genetic algorithm from Goldberg's book that uses fitness proportional selection. It is well understood that fitness proportional selections has problems for evolutionary algorithms. So when individuals have very similar fitness, the selection operator struggles to distinguish between the best ones and the worst ones. So here we have the definition of the SGA, and it falls into the general class of algorithms that Kristian described. So it's a generational algorithm that has a population of lambda individuals, and at each generation, it will create a new population of lambda individuals that replaces the previous one, and it does so by selecting two parents, X and Y, according to fitness proportional selection. So an individual X will be selected with a probability that is its fitness Fx over the sum of the fitness of the whole population. And then after it's selected these two individuals, it will create an offspring just by applying uniform crossover. So from each parent, it will choose a bit from parent X with probability 1/2 and from parent Y with probability 1/2. Then standard bit mutation with probability 1/n is applied to this offspring generated by crossover. And once lambda new offspring are created by this procedure, the new population replaces the previous one. So we want to show that this algorithm cannot even optimize the simple one max function that Kristian introduced earlier. So the function just returns the sum of the number of 1 bits in the bit string. So what do we expect the algorithm to behave on the function? So when individuals are very close to the optimum, so they've got many ones, it's more likely to flip a 1 into a 0 than a 0 into a 1. So we have, due to mutation, a backward drift. In expectation, we move away from the optimum. We don't expect crossover to give us any positive drift. And since fitness proportional selection struggles to distinguish between individuals when they're all close enough to the optimum, this selection operator will struggle to keep positive fluctuations. So we have a negative drift overall that goes away from the optimum. However, the analysis is complicated by the crossover operator because of the variance that the offspring distribution can have. While standard mutation individuals have small variance, have constant variance, crossover can actually create individuals that are very different from the parents. And the deviation in the order of square root of the length of the bit string is possible. And this is actually the difficulty in the analysis of crossover, that crossover can make very large jumps. So what do we want to do ideally? Ideally, we want to apply the negative drift theorem. So since we want to prove that the runtime is exponential with overwhelming probability, in runtime analysis, we apply negative drift theorems to do this. So what we have is we select an interval AB in the search space of length L, and we show that within this interval here, AB, we have a negative drift. So in expectation, we move by some value epsilon away from the target. So here's the target. And if in expectation, we move away from the target, and the probability that we make large jumps decreases increases exponentially with the length of the jump, then the negative drift theorem tells us that the probability that we finish in within exponential time in the size of this interval is exponentially small. So, however, we have two problems to apply this negative drift theorem to our generational genetic algorithm. The first one is that we need to decide in what position our algorithm is. Since we've got a population of individuals, we need to decide what state the population is in, what position it's in. And to do this, we use a potential function here. So we use an exponential potential function that sums the fitness functions of each individual using this exponential scaling factor here. So the function focuses on the top of the population, on the best individuals. The other problem we have is that crossover might not respect this condition 2. So the condition 2 says the probability that we do a jump of length j, apart from a scaling factor r here, that's not that important, the probability that we do a jump of length j decreases exponentially with j. However, crossover could potentially allow us to do jumps of length square root of the interval. So what we need to do is we need to control the diversity of the population. So what happens is we look at something called converged bits. So if all the individuals in the population have the same value at some bit position, so for example, the first bit is all either ones or all either zeros, so every individual has a 1, for example, in a bit position, then crossover cannot do anything with this bit. It cannot change its value. What we want to show is that if many bits are converged, then crossover cannot make these large jumps in the search space, and we can use the negative drift theorem to show exponential time with overwhelming probability. So what we do is we call diversity of the population the number of individuals that have got a 1 in some fixed position. So let's consider this random variable xt and look at, for example, at the first bit, and xt will be the number of individuals in the population that have a 1 in this first bit. Then what happens is that assuming that we have k individuals with a 1 in that bit position, then the probability that crossover produces an individual with a 1 as an offspring is going to be k over mu. This is just calculated by looking at the probability that both parents have a 1 in that position, or the only other option is that one parent has a 1 and another one has a 0. To do the maths and work out that's k over mu, which means that in expectation, if we've got k individuals with a 1 in that position, in expectation, the offspring will also have k1s in that position. So there's no drift really. We call this a martingale. However, due to the variance of the martingale, what happens is that we do actually move in the search space, and we can show that after, in expectation, all of mu log mu steps, we can do this by standard drift analysis. After all of mu log mu steps, we will either have all individuals with a 1 in that position or none of them. So the bit has converged, and then crossover is not effective there. And given that crossover can do at most square root of n progress in each step, if mu is not too large, in the order of square root of n, then one bit would have converged before the optimum is found. And if we assume now that we haven't got mutation, the algorithm will be stuck forever. So this analysis here was done assuming that we were using uniform selection, so that each individual is selected with probability 1 over mu. So what we need to do to generalize this is to to make it work for our SGA is that we need to generalize this result to the fitness proportional selection operator, and we need to take mutation into account. So how do we do this? And the main idea is that if we show that if the population size is not too large, many bits are converged, but if many bits are converged, crossover cannot make large jumps. So then the negative drift theorem is enforced, and we can use the negative drift theorem to show that we have that we do not reach the optimum with high probability. So the first argument is to generalize this idea to fitness proportional selection. So, and the idea is that if the population has small bandwidth, and by bandwidth I mean the difference between the best individual and the worst individual, the difference in fitness is small, then practically we can show that fitness proportional selection has approximately the same behavior as uniform selection. So practically we still have a martingale except for this small lower order factor if mu is not too large. And then we take into account mutation. And the overall proof idea is that mutation cannot disrupt the process that the idealized process that we've looked at up to now too much. So what happens is once we do have bits that are converged, mutation can recreate diversity by flipping them back. So if we've got all individuals with a 0 in the first bit, mutation can create a 1 bit in that position in some new offspring, but it does that slowly, and we still show that the bandwidth remains small and the diversity remains small. So the whole proof idea is that at the beginning we start with a population initialized uniformly at random that has got more or less n½ ones and then half zeros, and the diversity at the beginning will be small. But if the diversity is small, we can apply the negative drift theorem because crossover is cannot make the large jumps, as we discussed earlier. But then if we drift towards n½ then we can show that the bandwidth remains small, because individuals that have got less than n½ bits tend to have a positive drift towards n½ and if we know that individuals are not above n½ 1 bits by much due to the negative drift, the bandwidth will be small. And if the bandwidth is small, we can argue that, as we saw in the previous slide, that uniform selection behaves very similar to fitness proportional selection. So we have small diversity. And this process holds, we can show that with exponentially small failure probabilities, this process holds for an exponential time. And it allows us actually to show that the algorithm remains with more or less n½ 1 bits for an exponential number of steps. So this was just a general high-level proof idea to show you that it is possible to analyze generational genetic algorithms using crossover to show when they do not work with overwhelming probability.
So this is a summary of our tutorial. So we have introduced runtime analysis of evolutionary algorithms. So these are rigorously proved statements about the performance of evolutionary algorithms. So early on, this field considered typically very simple evolutionary algorithms like the 1+1 EA that don't have a population. However, practitioners are more interested in more complex algorithms that use large populations, crossover, perhaps various adaptation techniques. So we have described techniques for analyzing such population-based algorithms. So the first technique we looked at was drift analysis. So drift analysis is a very general technique that can be applied to analyze most stochastic processes. And if you read any paper about runtime analysis, it's very likely that you will see drift analysis used. However, it's not so easy to apply for population-based methods. So we described a very general technique called the level-based method that can be applied to analyze population-based evolutionary algorithms. So it's a very general approach to analyzing population-based algorithms where we consider an EA from the perspective of estimation of distribution algorithms. So many EAs or take our population, produce implicitly some probability distribution of the search space, and then sample the next generation. So this implicit probability distribution is typically a product of the crossover operator, fitness function, and other mechanisms in the algorithm. So this technique provides upper bounds on the expected optimization time of these algorithms. And we applied this tool to analyze complex evolutionary algorithms that use crossover, but that is subject to noise, and we also looked briefly at self-adaptation, where parameters, typically the mutation rate, is evolved with the individual. Then we looked at trying to see, okay, what is the limit of this non-elitistic evolutionary algorithms for very complex problems. So we looked at a very broad class of fitness functions that involved ruggedness, and we see that under what circumstances non-elitistic algorithms can be efficient in rugged fitness landscapes. Then we introduced a negative drift theorem. So this is a tool that we can use to prove when population-based methods are inefficient, when they need exponential time. So here it's important to look at the relationship between what we call the reproductive rate of the algorithm and the selective pressure. So here we can prove exponential lower bounds in various settings. For example, if there's too low selective pressure relative to the mutation rate. So we say that there is some kind of error threshold, so a balance between the mutation and the selection. So if it's too much mutation relative to the selection pressure, then the runtime can go from a polynomial to an exponential. Finally, Pietro described a result of or an analysis of a genetic algorithm using fitness proportional selection. So here is a complicated analysis using drift analysis, where we need also to take into account the variance or the diversity in the population.